Good evening, everyone. Welcome to the SMP Pandemic Seminar. Today, we are very lucky to have Ramprasad Saptharishi presenting. Ramprasad is a faculty member of the School of Technology and Computer Science at the Tata Institute of Fundamental Research, Mumbai. This is well known for its world-class research in basic sciences. Ramprasad is an expert in the area of algorithms and complexity. He is a part of the group known as IISC TIFR City Scale Simulation Team. This is a collaboration between the Indian Institute of Science, Bengaluru, and Tata Institute of Fundamental Research, led by Rajesh and Sandeep, who have joined us tonight. Thank you very much, Rajesh and Sandeep, for joining us. And now Ramprasad is going to talk about agent-based simulators for the study of COVID-19 spread. Thank you, Ramprasad.
Thank you. So this is a work that we have done in along with several of our colleagues in IISc, and I'll just briefly at least list out all the people who have been instrumental in doing this work. I mean, there's a whole host of people. I mean, the team in IISc is led by Rajesh Sundaresan, and the team in TIFR is led by Sandeep Juneja. But we are a varied group of people, faculties, postdocs, students, etc., who have helped. And we also have some assistance from sort of agencies with regard to visualizations and stuff like that. Okay, so basically we are going to try and study various epidemiological models that sort of helps us understand the spread of the COVID-19 pandemic. And this is the state of the world that's currently. And we're going to be specifically talking about the Indian context, where as of yesterday, we had about 300,000 cases and 9,000 confirmed deaths. Even though the disease seems to have spread through all sorts of cities in India, there's some large outbreaks, particularly worrying outbreaks that are happening in major cities such as Bombay, Mumbai, and New Delhi, Chennai, etc. There's been various restrictions in place and various relaxations that have happened as a result of more manageable numbers seen. And these have been adaptive, and these have sort of, different cities have adopted different policies with regard to these. Sort of to get a sense of how severe COVID-19 is, these are the statistics on the left-hand side. These are the statistics with regard to the influenza data. Sorry, it should have been influenza data in the US between 2017 and 18. And on the right is the COVID-19 related data until June 14. So we can get a sense of the mortality rates. But one thing to keep in mind is that, usually in a pandemic, it's not the mortality that is more worrying, but rather the exponential growth. Because if unchecked, then people who would have survived had they got the medical attention when they needed it, I mean, the healthcare system may be way too stressed to be able to provide the medical attention that they need. And this is why the exponential growth is perhaps more worrying. Okay. So the primary goal in these epidemic simulators is to try and help the people on the ground, which are these policymakers and epidemiologists, to try and make informed decisions in these difficult circumstances. Because until we can find some effective treatment or vaccines to address the disease biologically, we have to rely on these non-medical interventions or non-pharmaceutical interventions, maybe because you want to shield the more vulnerable population, or maybe because you want to sort of ramp up your healthcare capacities in order to meet the expected load and so on. And lockdowns work because they certainly reduce the contact rates and reduce the disease spread. But of course, there's a massive economic cost and hardships that are faced by people. So it's not a sustainable solution for the long term. So one needs to come up with strategies to ease out of the lockdown. So it's important to sort of keep in mind that, anything that we try to model for human behavior and so on is going to be inherently wrong in some sense. So there's this aphorism attributed to George Fox, which basically says all models are wrong, but some are useful. And so, but the right question to ask is like, even if the models are wrong, is the model illuminating and useful? And while I say this, I'll also sort of say that, maybe it's important to also keep in mind that when models are wrong, we should always be alert to what is importantly wrong here, because that would help us address the deficiencies of the model and maybe improve it to fit the reality better. Okay, so we'll talk very briefly about what we know and don't know about COVID, and then introduce some very basic SIR, very basic epidemiological models, starting with the SIR model, and constantly keep asking this question: okay, is there something that is deficient in this model? Can I augment it with something to better fit the reality? And proceed from there. And then I'll talk about some agent-based models and what specifically our agent-based model does, and some specific studies for the city of Mumbai. Okay, so let me very briefly say what we know and don't know about COVID-19. There seems to be a reasonable amount that we know, which is that it's quite infectious. R0 is estimated between somewhere 2 and 3. Transmission appears to be primarily through respiratory droplets, and it's largely a respiratory infection. But there's a lot of things that we don't know, or at least there don't seem to be good consensus for any of these things, which is that with regard to reduced virulence in summer, there's only circumstantial evidence for this. With regard to fomite or surface transmissions, we know that it was the virus has been detected on surfaces, but it's unclear whether those have caused transmissions to other people. It's also unclear if there are sort of fractions of the population which are sort of somehow immune to the disease for some reason. This also seems to be a fair amount of variation in how severely it affects individuals. With regard to asymptomatic transmission, there again seems to be no consensus. Earlier reports seem to suggest that this was perhaps rare, but recent reports seem to suggest that the answer is perhaps quite a lot. We don't even know what fraction of people are actually asymptomatic. There seems to be some disagreement about what does it mean to say asymptomatic, because often it is reported as people being asymptomatic at the time of testing, whereas this is not what is typically meant in the sense of asymptomatic, because these refers to people who never develop symptoms. And as a result, studies on this fraction seems to have a massive range of answers. So it's anywhere between 5 and 80%. And finally, we don't even know if people who got the disease and recovered, are they now immune to the disease, or at least in the short term? It is believed that, perhaps it is yes, because this seems to be the case for the other related viruses, but again, we don't have good consensus here. Okay. So with these in mind, let's just look at these epidemiological models, which is an attempt to try and best understand how the disease spreads in the real world. And we'll try and constantly keep augmenting it by addressing what is importantly wrong. Okay. So the SIR model is a simplistic model where there's a closed system of end individuals, and you put them into 3 buckets: susceptible, infectious, or removed. And you sort of think of them as a partition in the sense that at any time t, the sum of the people in this buckets will always add up to the population. And you start with a certain number of initial infections. This is the setup for the model. And then finally, in order to get the disease dynamics, you sort of make some assumptions. And the assumptions is basically to try and somehow homogenize the contacts, which is you say that an individual typically meets a constant number of other individuals in a day, and this is independent of the population. But you interpret this by saying that let's assume that every individual can meet every other individual, but with probability something like beta over n, so that this is sort of averaged out. And you assume that all these meetings are happening independent of others. And we'll further assume that whenever a susceptible individual meets an infectious one, there's a disease spread that happens. And there's also a spontaneous removal rate, which is mu, which is like the rate at which people who are infectious move to the removed category. And this leads to the following system of differential equations, which is very natural. Which is, the first thing is to just say that every infectious person has beta contacts, but only S over n fraction of them will fall into the susceptibles. So those are the new people who are going to get infected. And this gives you the well-known equations for the SIR model. And the thing to keep in mind is that this is a deterministic, once you set up this set of equations, it's a deterministic solver, and it's extremely fast. And there are very few parameters to really try and tune. Okay. And in order to figure out how can we identify deficiencies in this model and improve, one thing to keep in mind is that many of these diseases often have an incubation period in which an individual is exposed to the disease but is not yet started infecting other people. Okay? And there's usually a fair delay in when a person starts becoming infectious. And in order to account for this, you have this sort of the following improved model, which is called the SEIR model, where you add an extra compartment which corresponds to the exposed category. And depending on how you want to model it, you might assume that maybe people go from exposed to removed directly without ever getting to the infectious phase, or maybe you always pass through the infectious phase. This is all part of the modeling assumptions. Or maybe the modeling of the disease is less, you have a lot more states, etc. And all this will basically mean that you might need to introduce a lot more compartments in order to figure out this differential equation system correctly. And in fact, this was done. So at least this is one study that I'm aware of. This is the in-SISM epidemiological model, where you have nine compartments. The extra things are this IP refers to the pre-symptomatic, IA is the asymptomatic, and then there's the severe symptomatic, the mild symptomatic, and so on. And you need to build various transition probabilities between them and contact rates between them and stuff. And in this particular paper, they also introduce age stratification to keep track of the fact that contacts are often stratified by the age groups of the individuals as well. That's what we do. And so let's again ask the question that we have that has been helping us, which is that could we be missing something important when it comes to Bombay? One thing to keep in mind is that with regard to Bombay, so this is a rough heat map of the population of various wards in Bombay. Bombay is made up of 24 wards, and this is how the population is distributed across the city. But on the other hand, if you look at where they work, you notice that a lot more people are coming south for work. So there's going to be a completely different distribution. So this is one place to maybe suggest that homogeneous contacts is perhaps not best. The other thing is the notion of high density areas that are there in Bombay. So nearly 53% of the city lives in congested areas and so on. And and these are places where they need to access shared facilities, sanitation facilities, and so on. So the contacts in these areas are quite different from what may happen in the rest of the city. So all this perhaps suggests that homogeneous contacts is perhaps not ideal in trying to get a sense of how does the dynamics behave in Bombay or a city like Bombay. So if we wanted to address it, what would we be doing? We would basically maybe want to have a separate compartment for every ward. Maybe have a separate compartment in each ward for whether or not it's a high dense area or a low density area and so on. The extreme end of this is basically to look at these agent-based models, which is like saying that let's just build a compartment for every individual. And let's then look at the disease dynamics from that point onwards. Okay. So and there's this quote of von Neumann, which basically says that about why having too many parameters is perhaps not the right thing. But I'll try and justify why this is perhaps okay, because I feel that the pros that you get from this is perhaps sufficient justification, which is that we can really look at targeted intervention strategies. Like, can you do things like home quarantine? If a person inside a household is found to be symptomatic and stuff like that, we would like to isolate the entire household. And somehow maybe averaging it through the entire city is perhaps not the right thing to do. So this allows an agent-based model allows to do very, very targeted intervention strategies. And I somehow think that this is perhaps one of the pluses. I'll try and justify exactly why even though there are many parameters, perhaps that we don't tune that many of them once I discuss a bit about the details. So this is a very, very high level picture of what in general agent-based simulators are. And let me just transition into what our agent-based simulator does. So this is a disease progression data, information that we use. This is based off a paper from early March by Verity et al. Based on a bunch of clinical data that was available from China. And not all of them are just based on clinical data. Like, for example, things like the mean time for a person to stay in this exposed state. These are also based on some modeling parameters that they use. And so this is the transition that we model in our simulator, which is that a person stays exposed for about 4.5 days. And then the person becomes infectious. It's from this point onwards that the person will start transmitting the disease. And there's the short period where, like you don't really know if a person is pre-symptomatic or asymptomatic. So the asymptomatic people will transition into this other branch and go to recover directly. We assume that this is about 1/3. And as I mentioned, that we don't really have a consensus on what fraction this is. We assume that the symptomatics are perhaps a larger fraction to sort of give an overestimate for everything, because we believe that symptomatic people are perhaps, they spread more as a result of maybe more coughing or sneezing or whatever. So this is the assumption that we make. And then once you go to after the symptomatic phase, if the disease continues to persist, then the patient shifts to the hospitalized state. And maybe if the disease still persists, then the patient becomes critical, and then the patient is deceased. And the transitions from symptomatic to hospitalized, hospitalized to critical, critical to disease, we assume that these are age-dependent transitions. And this again is based on estimates that we have from the Verity et al. Paper. So this is the transition matrix that we use between the symptomatic, hospitalized, critical, and the dead states. But again, I want to stress that this is data that is based on China, and the clinical data from India is unfortunately still unavailable. And if we factor this table into our the Mumbai age distribution, the way the ages are distributed in the city of Mumbai, then it roughly translates to saying that of all the exposed people, only 2/3 of them are going to even become symptomatic, of which half of them are going to have mild symptoms. And the fraction of people that are going to require hospitalization is a really small fraction of the total number of people who are going to be exposed. So a large number of people are going to recover from the disease without ever knowing that they maybe ever got it, or maybe they had extremely mild symptoms for that to happen. Yeah, and this, which is also why a lot of these serology studies seems to show that the actual infections were perhaps not higher. So this is about the disease progression and what we use in our simulator. So let me then talk about how the dynamics for the spread works. So we model this as some sort of a rate-based simulation, where every infectious agent actually contributes a little bit of the infection to the workplaces. That's how we model it. So depending on how severe their infection is and so on, there are various parameters that you play in, and you contribute a little to each of these interaction spaces. And so therefore these common spaces will end up accumulating some sort of a cumulative infection coming from its members. And now every susceptible agent sort of collects a little bit from these common spaces, and then they change their state to exposed depending on how much infection was collected at that state. So all of this is done to try and approximate the idea that maybe you want to keep track of some sort of a pairwise interaction model between these agents. But the reason we do this in sort of a rate-based simulation is because this is something that runs in order n time, where n is the population size as opposed to order n squared, if you were to do some sort of a pairwise interaction. So in one sweep, all the infectious agents contribute to the facilities, and the second sweep, all the susceptible agents pick up and decide to get infected or not. So that's on a high level what happens. There's a whole bunch of heterogeneity that we also maintain in terms of contacts. Like for instance, the heterogeneity will show up because the spread that an agent has is going to depend on whether or not the person goes to school, the person goes to maybe takes public transport, etc. And the fact that a person stays in the high density area or the low density area will sort of change their contact rates within these places. We also try and keep track of some sort of a severity induced absenteeism, that someone with more severe symptoms is more likely to stay at home, and so on. So these are things that will reduce contacts in their workplace or school, but might increase contacts at home. And this is to try and, there seems to be studies that suggest that that maybe 20% of the infected likely have caused 80% of the infection. This also seems to be that the infectiousness seems to vary rather wildly from people. So we also try and model infectiousness at, maybe I shouldn't say fat tail random variable, but as a gamma distribution or something. So this is some additional details of how the spread is modeled in our simulator. Okay, this is at a high level what happens on the simulator, and let me now talk about how we model interventions. The way the simulator works is that there are some basic interventions that we keep in mind, and then the more complicated ones are sort of composed versions of these. So probably the thing is, like, we assume that during a lockdown, the rates that we assume is that the household rates are double because people stay at home more and workplaces are closed. But we assume there's about 25% leakage for essential services and so on. And community interactions, etc., we assume reduced by 75%, etc., etc. So this is, and we try and separate this between what households are compliant and what households are perhaps not compliant, and those that are not compliant, still they have increased sort of contact rates with people. And there are a few other things that are taken into account in our simulator. One of the things is case isolation, where we assume that after 24 hours of showing symptoms, the symptomatic individual decides to stay at home for 7 days and reduce their non-household contacts by a fair amount. So this is one thing. And the home quarantine is, like, you're doing the same thing, but you also extend it to all the other household members. And they are going to remain at home for 14 days. The reason 7 days was important was because, like, maybe by 7 days, if a person has started showing symptoms, maybe either you recover in 7 days or you're likely going to end up in the hospital. Whereas people who are at home who may have recently caught the disease, maybe it takes longer for you to figure out whether or not you have truly been infected. So which is why we have this 7 versus 14 days. And we can also do things like, all individuals who are aged above 65 years of age, I mean, they reduce their community interactions and so on. So these are some of the basic interventions, and what the code actually does is it lets you really customize this by providing a file as input and saying that on which dates, what are these basic primitives do you want to be active at that point, and so on. So this is what we do. So one thing I'll also mention is that in Mumbai in particular, there was an official directive that from April 9th onwards, people should start wearing masks. We don't actually know what the precise reduction in transmission is, but there seems to be studies with regard to influenza from earlier that seems to suggest that this is perhaps a reduction of about 20%. And this is a factor that we take in our simulator, but again, this is something that can be customized if we have better data for how this works. So that's what it works. So that's how these interventions work. And I want to talk about one important thing which I think is important, which is something that we model, which we call containment zones. It's like some sort of an adaptive lockdown at a far more local level than at a city level. So to try and model this containment zone policy, what we tried to do was we tried to understand how our local authorities seem to work on the ground. And so what we learned was that, there are points when there are buildings where if you find a positive case, or if you find a certain threshold of positive cases, then this building is completely sealed off. Like, which means that, the movements that are in and out of these areas are just heavily monitored. Only essential services are allowed to enter. And in high density areas, this is particularly more relevant because these containment zones are large clusters of buildings where these sort of restrictions apply. And in order to try and get a sense of, how perhaps this may be modeled on the ground, the way we model it, we sort of say that, let's assume that each ward is going to be partially locked down based on the fraction of the population that is currently hospitalized. So if the ward does not have that much of infection, we assume that the ward is completely accessible. That is, people can move freely in and out. But if the ward has a certain fraction of hospitalized cases, we assume that the ward is going to get more and more closed down, depending on how many people are currently hospitalized in the ward. So as more and more people get recovered, the ward is going to be opened. And in terms of just pictorially representing it, this is sort of roughly how we model the adaptivity. We assume that there is some sort of a containment leakage, which is like getting a sense of what is the largest extent to which you can close this ward. if we believe that, we cannot reliably, possibly try and close the ward for more than 50%, then that's what our leakage is going to be. And the threshold basically says at what point do you reach this maximum. And these are some parameters that we maybe can, depending on how the ground reality seems to be, that, these are parameters that could be tweaked depending on that. So this is a bit about the containment zones. And finally, let me also mention an important aspect of Mumbai, which is the public transport system. So the trains are an extremely essential part of Mumbai. So there's about 7.5 million passenger trips on a normal working day. Like this is our old statistics, and we know that 90% of the working population actually use the trains to commute to work. And fortunately, the thing is we don't have real data to calibrate contact rates on the trains. So we are forced to make further assumptions. And the way our modeling works is like we sort of assume that there are about there's about one effective one every minute of contact that a person has on the train. Again, we don't know if the answer is if this is the right answer, but we try to play around with these parameters and point out all the possible scenarios. The other thing, the reason we don't have data about contact rates on trains is because in Mumbai we believe that the initial infection was largely imported, in the sense that these were people who traveled from abroad, and that was the initial seed. So we believe that the trains didn't play an important role in the initial part of the infection spread. And very soon, actually, in Mumbai, trains were closed. So we actually have no idea of how much did the trains contribute to the infections. But this is the assumption that we make, and this is what we work on. We just try to map it to how many contacts we expect to happen inside a household, and we just care about what this ratio is. Okay, so this is what the details is, and so there's clearly a lot of parameters that have been thrown, and a lot of these parameters are sort of assumed. There's we believe that this is the right things, and there's some of them which are corroborated with other pieces of data that we have. But I want to specifically talk about how is the model calibrated. What are the parameters that we change in order to fit the observed data? Because I believe this is a question that's going to be on the back of the minds of various people. So the parameters that we try and calibrate are primarily the contact rates, which is the contact rates that happens inside a household, inside a school, inside a workplace, and inside the community. And we seed our simulator with about 100 infections. And what we do is we just try and adjust these contact rates for the data until April 9th. So the reason until April 9th is that this is the part where we believe that lockdown effects have not yet taken. It has not yet shown in the observed data. The official lockdown was on March 25th. And this is the data of, this is the cumulative fatalities that have been plotted. And there'll be typically about a 20 or 25 day delay between any intervention that is imposed and when you start looking at the effects of that at the fatalities curve, because of the way the disease progresses. So therefore, we believe that somewhere around April 9th or something is when maybe lockdown effects have not taken place. So we just run our no intervention simulation and try to calibrate these beta parameters. So that it matches the growth rate of the observed fatalities. The other thing we try to do is somehow make sure that there was equal amount of infection coming from homes, workplaces, and communities. And this is based on past cohort studies for flu and about how the flu was spreading and what sort of contribution did these interaction spaces have. So those are the two things that will basically determine what the betas are. So once you fix these betas, the betas are now fixed. So the contact rates are all fixed. And the next thing is to do is just align, when you say start the simulator, like when is the simulator starting? So you align the start date so that it fits the curve for Mumbai. So that's what you do with regard to calibration things. Okay. In order to get a sense of what happens in the lockdown, so the primary thing seems to be that, it's very hard to get a sense of what is the compliance of various individuals in the city with regard to the restrictions imposed. So since we don't know what the answer to this is, we just we try out various parameters, and it turned out that around somewhere around 60% to 70% is what matched the fatality rate once we established the lockdown. And there are some sort of post hoc justifications that you can come up with, which is like there are these Google mobility reports and so on, which seems to suggest what are the reductions in these in contact rates and so on that have been happening in actually the state of Maharashtra as a whole. And so that's one thing. So we assume that the way we set up our simulator is that there is a slightly lower compliance that we assume the high density areas, to account for the fact that these are high density areas often have individuals that don't have the luxury of individual sort of facilities, such sanitation facilities and so on. So they are forced to use these shared toilets and food distribution centers even during lockdown. So our definition of lockdown should mean that you have far reduced contacts in these places. So to adjust for this, we assume a slightly lower compliance in this. So in terms of what we actually calibrate to, so these are the only, so we calibrate to the initial betas, and then we calibrate the compliance levels. And from this point onwards, whatever the simulator gives is what it gives. Okay, so this is what how our simulator roughly works. The code is publicly available, so it's there on the GitHub repository, along with a rather detailed instructions of how you can perhaps run it on any other place. So the city generator is written in Python and the simulator in C++. And yeah, I mean, I'll encourage people to work with it. You know, maybe if there's something that they feel that this can be added or some modifications, then we'd be interested to know. So we also built, I mean, this was actually thanks to SAP, which did a revamp of the original build that was done by the ISC group, which is like a browser version of the simulator, which actually runs on a city of about 100K. Because this is small enough that you can actually run it on a browser and it doesn't take much. So it's very similar to the actual simulator that we have, where you can set various parameters that you want, set the intervention that you're interested in, and just say run, and it basically runs the simulation and so on. So I'd encourage you all to try it out. It's a pretty fun exercise. So there are a few specific interventions that have been implemented, but I mean, if there's more interest, then we should be able to add more to the system. So this is what I wanted to say about a high-level picture of how our simulator works. And now let me talk about perhaps two specific studies with regard to the city of Mumbai, which was to try and help our local authorities once we had guidelines about how they plan to open up the city. So the details of this is available on the preprint, but I'll just mention some very, very specific things. Which is that one of the things that we wanted to study was that the intention of the local authorities was to open up the city, but with sort of slowly increasing work size capacities. So the plan was that May 18th was the end of the sort of lockdown, so to speak, but there were still severe restrictions that were put in the city of Mumbai because of its high infection rates. That offices are only allowed to operate at around 5%, and this wasn't even all offices. So the official Ministry of Home Affairs guideline seems to suggest that certain kinds of offices can operate at around 5%. And we wanted to give some sense of projections as to what would happen in the subsequent months to try and prepare the healthcare system for this. So we ran two sort of scenarios. One where we assumed a lower attendance profile, which is like you assume that the June occupancy is going to be about 20%, and then it becomes 33%, and then 50% in the month of August onwards. Or a slightly faster increase in attendance, which is that you start off at 5, but then you make it 33%, 50%, and 7%. And throughout this point, we assume that there's going to be case isolation, there's going to be home quarantine, and there's going to be social distancing of the elderly, and schools and colleges are going to be closed. So these are some things that we assume that, again, when I mean the case isolation and home quarantine happens, it's only among compliant households. So we're only assuming that about 60% of the households comply to these sort of preventative measures. Okay. And then we run this through our model, and these are the sort of curves that you get. And I'll specifically point out about the sort of weird sort of oscillatory behavior that you would notice. And this is a result of what we think is happening due to the sort of containment zones being in place. So what technically is happening is that the infections are rising, but certain wards are getting closed down, and that is slowing down the spread. So then the containment levels are again becoming getting lifted, but then maybe infection rises again, and so on. So this is roughly, so this is a weird behavior that you would not see in a model that does not have these sort of adaptive measures in place. And I will also use this to sort of say that maybe a litmus test to us will actually be what is going to happen in the first week of July. That will perhaps tell us whether we are modeling this containment zones reasonably accurately or not. So this is the number of regular hospital beds that we require. And I should also mention that all the graphs that I'm going to be showing was actually a result, it's an average of 10 runs. It was actually 5 runs on 2 separate instantiations of the city. And I don't know if it's very visible, but there are these error bars or something which really amount for what is the variation that we see among these 10 runs. So that's what that refers to. This is the standard error about the mean or among these 10 runs. Okay, so this is the number of daily hospital beds that we'll need, and this is the number of critical beds that we need. And as you might expect, there's going to be a slight shift in the peak because, I mean, that's how the disease the progression works. And then this is the number of cumulative hospitalizations, which we believe is a reasonable proxy for the number of confirmed cases, though it's not quite so. We believe that the way cases get discovered in our city is that often there is someone who requires, someone who has fairly severe symptoms that the person requires hospitalization. And then the person approaches the hospital because they need this medical attention. Once that happens, there's a lot of contact tracing that happens around the person. So you look for their close contacts, you maybe test the close contacts and so on. So those are the other discovered cases that you're going to find. But from our simulator, we currently have not implemented anything to do with sort of contact tracing and so on, though it's on the cards. And this is the reason why we don't seem to understand how exactly to fit with the current number of confirmed cases, because there are 2 increasing factors that seem to play into it. One is the increased infections that you see, and the other is the increased testing capacities that we are seeing. So since this is something that appears to be harder to control, we focus completely on the fatalities for all our calibrations because we believe that that is a more reliable trend to keep track of. So this is this. And then this is the number of fatalities. I'll also mention that there is this weird change that has happened in the last few days, which I'll specifically try and address. So until about 4 days back or something, I was quite happy with the way the simulator was predicting, was fitting the data. And then the last about 4 days or something, there's just been massive spikes in the number of reported fatalities. And there seems to be some sort of unofficial reports to suggest that, there has been some misrepresentation of data of the previous fatalities. And therefore, there's some adjustments that are due. And so on. It's unclear exactly how these curves are supposed to change and whether we need to recalibrate what we have done so far. But this is what it is. So, okay. So this is the study with regard to the attendance profiles. And then we also wanted to keep track of, what this containment zone leakage, what's the right way of modeling this or rather, what is the right leakage that sort of represents what is happening on the ground? And we don't know what the answer to this is. So what we do is we actually plot various levels of leakage to sort of get a sense of how do these things change. So, so containment leakage of 1 refers to the fact that there is just no adaptive containment in place. So it's not like wards are going to get additionally locked down as a result of increased hospitalizations. And as you might imagine, this now has a peak and then it drops off. But as you sort of a rather mild containment leakage, where you're sort of saying that you tell yourself that you're never going to be able to close more than 50% of the ward, and that this threshold is reached at a certain point. And but even that seems to make a massive difference with regard to the requirements with regard to hospitalizations or critical beds that are necessary. So these are the curves for for various things. And anyway, for people who are interested, you can look at the paper also for this. Okay, so now that I have said all this, I want to now talk about what are perhaps things that we are importantly missing, because this is something as I said earlier, I think this is something that we should constantly be aware of this, so that we can try to address the deficiencies of the model. And one big thing is this notion of what is called sensitivity analysis, which is that there's a lot of parameters that fit into the model, or rather, a lot of parameters that sort of are fed into the model, and like how sensitive is the model to these parameters? Like if we were to slightly change them, how much would the predictions change? And we already have things in the pipeline for this, and hopefully this is something that should be added soon. There are other factors which seem to affect these numbers quite a bit. This seems to be the comorbidity data and the gender of the individuals, because especially in India, I mean, a large part of the cases that have been reported turn out to be male. And it's also because the interaction patterns among, it seems to vary rather differently between gender. And comorbidities also play a big role in how the disease progresses for these individuals. But there is some lack of data on, or rather lack of data that we want on in order to accurately model this. But we are hoping that this is something that should be added soon. The other thing is, one thing that a simulator does not do is get a sense of what are the economic costs for various interventions that are being proposed. So this is out of the scope of the simulator, but what we instead can do is like, we can have a sense of sort of quarantine statistics or curtailment statistics, which is like what number of people who are actually not infected are being forced to stay at home with regard due to these various interventions in place. This is something that we can get from our simulator, but unfortunately, the economic cost is something that is outside the scope of what we can do. So this is what is missing. But now let me talk about some aspects that I believe are importantly wrong. One of the things I mentioned is estimating the number of cases. And as I mentioned earlier, is that this is something that depends a lot on what is the testing strategy that's currently being used. And in India, actually, this testing strategy has itself been evolving. There was a point earlier when you would only test people who have had travel from abroad or close contacts of travel from abroad. We were not even testing people who were asymptomatic and so on, but these all changed with time. So these changes that are being done in policy is going to greatly affect the number of cases that we observe. And it's due to these things that we are not able to really estimate the number of cases that we see. Okay, so that's one thing to say. The other thing I want to point out is that we seem to be fairly off in estimating the number of recovered people. And the reason I believe why this is happening is because I think that perhaps people in India are coming to the hospitals later than what is being suggested in the disease progression studies from China and so on. And it would be really, really useful if we can get this sort of hospital line information from hospitals in India, which is to say that when did a person come to the hospital? How long was the person in the regular hospital? After how many days did the person become critical? And so some sort of information about this, so that we can get more representative data with regard to this. And then finally, something that's just bothering me is about what is happening in the last 4 or 5 days, and these sort of corrections that are being suggested. So for this, I believe that we just have to wait and see. But I'll still say that, one of the things to keep in mind is like what really happens in the first week of July, because I think this is one place where the numbers predicted by us and the numbers predicted by perhaps other models seems to vary a fair amount. So it will be interesting to see whether the numbers continue to rise in July or the numbers sort of stabilize by about July first week or something like that. And yeah, so this is what I wanted to say. I'll just conclude by sort of just summarizing and say that we looked at agent-based models, and which allowed us to have some sort of a heterogeneity at the level of individuals and in the interactions that they have between them. The main gain is to try and look at very, very targeted intervention strategies and get a sense of comparing two different intervention strategies. And some observations to have is that, the sort of adaptive ward closure seems to be rather effective as opposed to a complete lockdown. So that if you can do this at a more localized level and you close down areas which are perhaps more problematic, this seems to have a pretty good effect. And we tried to estimate the effect of trains in Mumbai. But again, as I said, we don't really have good data of the contact rates on the trains. And sort of also pointed out certain deficiencies of our modeling and maybe what to look out for to try and see at what point do you realize that, maybe there's some adjustments that are in place because we don't seem to be like effectively capturing what's happening in reality. So yes, that's it. That's all I wanted to say. Thank you.
Thank you very much, Ramprasad. That was a very, very interesting talk. Thank you. So we normally have this tradition. I just count back from 3 to 1 and everyone gives a bit of a virtual clap just to say thank you. So 3, 2, 1. Okay. I think everyone said thank you. Yeah, thanks again. Does anyone have any questions that they'd like to ask Ramprasad while they've got the chance? Okay, so
Can I ask?
yes, Charlie, go ahead.
Hi, thanks for the talk. It was very interesting. I must first apologize. I'm responsible for a technical problem with the recording, so we only recorded from about 20 minutes in. But
okay.
Later, so it's a bit too bad because it's a nice complete talk. So about your simulator, are you continuously now adapting model parameters of the simulator to do kind of a best fit to what has been, or are they fixed?
Yeah, so the thing was, so before we introduced this notion of containment zones and so on, we were thinking about the compliance is a little larger, about 70% or something. So because at that point, the only parameter that you're tweaking is the compliance. And then on talking to a few people, we realized that no, there are these containment zones that are being, there were a lot of containment zones that were being placed, especially in the high density areas, which were to address the spread there or something. And we were asked if, no, this is something that we are modeling. So then we said, okay, we don't really know what this number ought to be. So then we introduced this notion of 0.25 as the leakage. We don't know if that is the right thing. And as a result, the compliance had to be a little lower. So that was the only change that happened. But this recent spike of 4 days that has been happening, we have no idea what's going to happen. Yeah, whether these numbers have to be adjusted right from the start or, yeah.
If I may, I'll just make one comment.
Yeah.
So this recent spike is also in the change in philosophy of reporting the number of deaths. So earlier it was reporting deaths which were due to COVID, and now suddenly it's deaths due to COVID and deaths with COVID. So that's why the number has increased. But I think we're waiting for officials to clarify things, and then we'll recalibrate the model. We hope things should.
Yeah, but I guess the worry, not the worry per se, but it also seems to be that this would mean that the trends that we are going to see from now on is going to somehow incorporate this adjustment. And it's unclear exactly how we are going to keep track of this slightly changed trend.
Sure.
I have a question.
Yeah, I said it.
So I have noticed that the number of recoveries past few days, suddenly a lot of recoveries there in India. And what data you are following to model recovery rate?
So from the simulator, the disease progression already says whether or not a person has recovered. So that's one thing. But in order to capture the recovery, since we believe that the true cases must be people who reach the hospital and then you do some contact tracing around them, maybe a good proxy for the recovered would be like, what can you say about the recoveries that reach the hospitalized state? Now, technically speaking, this should sort of look like the number of recovered cases that we see, that we observe among the confirmed cases. But it seems to be that the the Mumbai observed recovery curve seems to be far lower than what we expect should happen from our simulator. Now, one reason could be that, maybe people are coming in to the hospitals when the disease is at a much more severe stage. Maybe that's the reason why the recovered rate is a little lower. So it's unclear at all. It would be very, very useful if we can get more specific data that's happening as to what is happening in Bombay, so that we can update these parameters accordingly. To us, I think that this should ideally be a tool where there's a lot of parameters that we don't know what these things are. But this should be a tool where epidemiologists who have better understanding of what are these numbers on the ground, and perhaps this is a tool that can assist them in better, make calls on what do you need to do in situations of this sort. So we are unfortunately having to work with the clinical or other studies that are available, which is actually not for India, but it's for China and other places. Yeah.
Thank you.
Rajiv, I'm joining.
Can I ask a practical question?
Yeah, please. Yeah.
So you've got tens of thousands, if not millions of agents here. How long is the real-time period that you roughly simulate, and how long does that take to run typically?
Okay, so we generally do the simulations. All the graphs that I had was a simulation for 200 days. So that was the period that we were simulating. It comes to till about, I think, September 3rd, if I remember right, and that's how long it comes. And on my local machine, a single run takes about 40 minutes. This is if I run it on my laptop. But we actually have a compute cluster in our department, which has multiple cores and so on. So in that, we can actually run something like, I think 15 runs in parallel that happens in about 20 minutes or 25 minutes or something.
That's awesome.
So, yeah, so that's roughly how much time it takes. And we usually run these things overnight, and the next morning we just collate the data and create these graphs.
So just to add to that, we have 12.4 million agents running.
Oh yeah, the city is of 12.4 million agents. So for example, just the individuals, the city generated files is already of the order of about 3.4 gigabytes or something.
Okay, so you're doing an amazing job here. I work in commercial simulation. I spoke with colleagues. You are blowing all our estimates of is this even possible so out of the water. I'm amazed.
Thank you. Yeah.
Thanks.
Did anyone else have a question over here? I had one final question.
Yeah.
If no one else wanted to ask a question, Ramprasad. I can see you've used this on the example of Mumbai and Bengaluru. Are there any plans to extend this to looking at other cities or states?
Okay, so actually this is something that we are currently working on, and in fact Rajesh's group in IAC have particularly been doing this, which is to try and apply the same model on the data that we have from, say, Wuhan and New York, to try and get a sense of, how good is the model in predicting it there. Because we somehow believe that in principle, the principles used in the model we believe should be similar there, even though if the contact rates are going to be slightly different. So that's currently on the cards. So those are two places that that I know we are running simulations on. Hopefully those reports should also be out soon. The other cities, so far we have not run these things, but I'm hoping that, with maybe there are other cities in India which we should be able to run, because at least we know exactly what data we got from where with regard to Bangalore and Mumbai, because the India census is available in very similar formats. So maybe this is something that we should look towards doing.
Yeah. Okay. Would be nice if you could keep us informed. If you have time, just send us an email. Let us know.
Yeah, sure. Yeah.
Were there any other questions from anyone? I guess one more time we'll thank you very much for such a very interesting talk. That was really great. Thank you. And
thank you so much.
Thank you.